Okay, let's get started. So, lots of things to hand back today, and make sure to turn in your quiz 7 and your homework 2 today. I have your quiz 5, quiz 6, and homework 1 if you haven't picked it up. So, um, okay, so I have homework 3 is posted on Slack, so you can get started on that, due next week. Are there any questions about anything? Yeah, the projector's still not working, so we'll just have to deal with what we got for at least for now. So any questions since last time? Yeah, so actually I should say, for homework 1, most everyone did well. There are just some things that people missed, like they wrote something down and didn't justify why it was that way, or they left out a state that they shouldn't have left out, like minor things. So I was pretty pleased with everyone. Just take a look at the comments that I provided you, and of course, if you have any questions, always ask. But you should not be worried about the score if it happens to be a low score, but rather be worried if there's a lot of things that you're missing. And if you see that the comments have some kind of pattern, like you're missing the same thing over and over, then you should be able to rectify that in the future. Remember, it's perfectly fine to miss a point once or set of points once. It's a really terrible idea to miss the same points twice or more. So if you miss something, try to not miss it in the future. Okay, any questions though? So luckily, we're actually ahead of where I thought we would be. So maybe we should look at and kind of slow down, or maybe just keep at the pace we're going if everything's good with you guys. So what I wanted to do was to do some more pumping lemma examples, because that's the thing that students have the most trouble on, at least in the beginning. They have the most trouble with this material, so we might as well do more of it. You guys are okay with that? Or do you want to do something else? Yeah.
We ended the class right before we were about to explain the pumping lemma completely, proof, how to write a proof for it. We were on step 3 of 5. I think.
Oh, okay. Let's see. Oh yeah. Okay. So let's actually. What I'm gonna do is I'm going to. Thank you for reminding me. I did not remember that. So I'm gonna copy this over, and then we'll continue from where we left off. I think that's a good idea. Thank you. So this is where we were last time. We did the language 0 to the n, 1 to the n, and we showed that it wasn't regular. Now I want to look at this a little bit different language, not the same, but slightly different. And we want to show it's not regular. So the recipe, Ryan's recipe for this, is to assume to the contrary that L is regular. So just start out. Let's just assume that it's regular, and then eventually we'll get a contradiction. And the contradiction we will get is that we'll try to pump a string by putting more copies of the Y part in to get a string that's not in the language anymore. Because the lemma says that you will always stay in the language, but if we can show an example where you leave it, then that contradicts everything. So here, once you assume that it's regular, we know from the pumping lemma there exists a pumping constant P for L, just some number. We don't know necessarily what it is, we just know there's a constant for it. Okay, so then we pick this string right here. So why did we pick this string?
Because its length is greater than the pumping constant.
Yeah, it has length greater than p. Why don't I just pick the string 0 to the p? It has length at least p. You notice how insistent I am about this. Yeah,
No longer the language.
it's not the language. So remember, the two important properties are it's in the language and it has length at least p. If you don't satisfy one or either one of those, then you can't really say anything from the pumping lemma point of view. So this one is a non-starter. Now the thing is, I wish I could say that if you pick this string, you will always succeed in proving that the language is not regular. That's not always true. So, in fact, we may even see an example of that today. So there's kind of an art to doing these that you understand after doing it several times. So the suggestion that was brought up last time of, well, if there's an n in the exponent, just put the p in the exponent. That's actually a really good strategy most of the time. Sometimes it's not necessarily the right one, but it's often very close or correct. Okay, so I guarantee this string will work. So let's see. Well, we pick this string. What do we need to do next? Well, remember, what does the lemma say? It says there is a way to decompose the string into 3 pieces. Right, so, but do I need to test 1 decomposition or 2, or do I need to do all of them? We need to do all of them, because the lemma says there exists a way for it which it works, but we want to show that that's not true, which means that no matter what way you decompose it, it'll always be false. Okay, so what are all so we need to look at all I'm just going to shorten it to decomps of W into X, Y, Z. And then we'll write X is equal to something, Y is equal to something, Z is equal to something. So what are the possible decompositions of this string? Well, remember the first, go ahead.
That x is equal to 0 to the alpha greater than or equal to 0. That y is equal to 0 beta, because you know the xy has to be less than p.
Mm-hmm.
And z will be the rest of it, which is going to be 0 to the p minus alpha minus beta to the 1 to p.
Exactly. So the great thing about this string is the first p characters are all the same. So I know x has some number of zeros, I don't know how many. Y has some number of zeros, at least one of them, but I don't know how many otherwise. And z is the rest of the string. So I could, and this would work, I could, for example, pick w equal to 0 to the p over 2. Yeah, that'd be fine. Then 1 to the p. I could pick that one if I wanted to, and it would work. You would be able to show that this language is not regular with that string. What is better about the one we picked versus that one? Well, what does the x part contain? It can contain zeros and ones. So if we pick the red string, then the problem is the x part could be either only zeros, or it can have zeros and ones. And the y part could be is just in the zeros, or zeros and ones, or just ones. So the problem with that string is that there are more cases to deal with. You can prove that it still works, but you have to deal with more cases. We like things simple here. One case is as good as it can get. So this is why the one we picked is much better, because there's only one possible case. Okay, so then once we're looking at all decompositions here, what do we need to do after that? Pick an I, and then what do we want to show using this number I? What is the I in reference to? Was there? Yeah, the number of times y appears in a string. And what do we want that string to be? So such that x, y to the I, z, what do we want to happen? Was there? Oh, no, not necessarily. That would mean setting I equal to 0. But what is the property of this string that we want to have?
Being in the language? No.
Yeah, not being in the language anymore, right. Because the lemma says that it'll stay in the language no matter what value of I you choose. But if we can show that you leave the language when originally the string you started out with was in the language, that contradicts everything. Okay? So we just need to pick a value I such that the resulting string is not in the language anymore. So any choice of I that you want to do?
0.
0. It'll turn out any value other than 1 will work for this one. So let's pick I equal to 0.
Actually, you said any value? So
Any one of them would work in this for this particular language in string.
could we possibly do 2 then?
We can do 2. Yep, that's again, that's a perfectly valid one. The result will be exactly basically the same. The resulting string will be different, but the conclusion's the same. So this says to look at the string x, y squared, z. So y to the 2, z. That's what the I equals 2 says to do. So this string will, if we just substitute the decomposition we're looking at, well, the x part is 0 to the alpha. There are 2 copies of y now, so that's 0 to the 2 beta, because there are 2 sets of beta zeros, because we picked I equal to 2. And then the z part at the end. Oh, 1 to the 2p. 2p or not 2p? Okay, well then what do you think we'll do now? Well, yeah, we have 3 runs of zeros. Well, they're all next to each other, so let's just put them all together. So when the dust settles, how many zeros are there left? So what are the things that cancel here?
These.
One of the betas cancels, so we have remaining. We have a positive 1 beta. And what about the alphas? The betas killed the alphas. So we have a p plus beta left over, and then 1 to the 2p. So what is the thing that we have to check about this? Could this string be still in the language? Because if it is, then we just did a bunch of work for nothing. So could this string be in the language? And if it is, what has to be true? Right. So the only way that this string would be in the language is if this exponent right here, so it's in L if 2 times p plus beta is equal to 2p. That's the only possible way it could be in the language.
There's a contradiction if beta is 0.
Right, exactly. Which is equivalent to saying beta equals 0, which is, of course, as you say, a contradiction. Cool. So then we can conclude then, as the last step, that L is not regular. Yeah.
So this process is pretty standardized for most of the
It's pretty standardized. We're going to actually do more examples and we'll see this type of thing. More interesting examples. But yeah, it's pretty standard. I think on your next homework, I'm not sure, but at some point you'll see a different way of approaching this, just using closure properties. So it is possible to show that a language is not regular and just avoid the pumping lemma altogether, just by using closure properties and getting a contradiction in the same way. So, and that's actually way easier than doing this, but it's just, the pumping lemma is pretty much the only way we'll see showing a language is not regular in this class. There are other ways outside of what we're going to do here. Any other questions? Okay, so let's actually do a more interesting example. So I'm going to call this L, I guess. So this language is not going to have just zeros and ones in it. It's only going to have zeros. So so instead of being a binary language, it's a unary language, meaning it only has one character. So this language is 0 to the n squared, where n is at least 0. So another way to think of this is all of the perfect square lengths of strings. So as an example, so 0 is an L, 4 zeros is an L, 9 zeros is an L, etc. Okay. So I'm going to actually give a heuristic for why this is not regular, which is I'm not sure if you did this in 290, but notice that the differences between the squares keeps increasing. So between the first two, I guess the empty string is in there too, but it's not really that important. So between the string of length 1 and 4, that's a difference of 3. Then the difference becomes 5, then the difference becomes 7, then 9, then 11. So the differences are increasing. And because of that, since the DFA has a behavior of if you have a string of a certain length, you'll return to a state twice, then that means that there needs to be some kind of regularity in the differences in the lengths of the strings, which is actually kind of how the proof goes too. So when there's not such kind of a regularity between the actual strings in the language, then that is an indication that it's not regular. But this one's not regular, and we'll prove it. So this is not regular.
Why is the empty string?
Because if I choose n equals 0, that means choosing the character 0 no times at all, which means it's the empty string. Yeah, so that's why that one's in there. Although for the proof, it won't actually matter. One interesting idea that you can try is if you have a non-regular language and you either add or take away a finite number of strings from it, then you will still have a you'll have a non-regular language. So it's not like I can add 3 strings into this language and it suddenly becomes regular. So that's actually not that hard to prove either. But let's look at this, because this proof is insanely cool. In fact, I think it's my favorite proof in the entire class, in the entire course, which is, it gives me goosebumps every single time I do this proof, believe it or not. So let's prove that this is not regular. So how do we do that based on what we know? Assume it is. Yep. So let's assume L is regular. And from that, what do we know? Other than that there exists a DFA. Yeah.
Constant P.
Yeah, there's a pumping constant P. At this point, we'll have done this so many times that I'll just say exists a P for L. Just to shorten it. But yeah, there exists a pumping constant P for L. Okay. Now what do we do? We got to choose a string. What are the 2 properties that string needs again? In the language and length at least P. So any candidates for this language? So what string do you want me to choose? I'm counting on you guys to make this easy for me.
0p squared.
P squared. Okay. That's in L, and is at least P? Certainly. Cool. So that's good. So do you remember in lab 1 when I asked you that question about if you have, so let's have a little thought bubble here. So if you have beta between 1 and P, could P squared plus beta be a perfect square? You remember that one? You remember why I asked that? It's this proof. Dun, dun, dun. Okay. So let's look at this. So the reason why I asked that, as well as the question of P squared plus I times beta, the values of I that work, is exactly this proof. So when we looked at that, well, what did we conclude about P squared plus beta? Was it ever a perfect square? No. So for that reason, which value of I should we pick in this case? Because we need a P squared plus beta length, yeah.
Between I and P.
There's a concrete value. So look at the last proof we did. We ended up with how many zeros on the front? We ended up with P plus beta of them. Well, how do I get a plus beta out of this one? Yeah, choosing I is equal to 2 also. So if we choose I equals 2, and I'm actually avoiding the decompositions here. Why do you think I'm avoiding them? There's a very simple reason. Oh, what's there? Yeah, there's only zeros. So it doesn't matter what the decomposition is. Yeah, so that's why. So if we choose I equals 2, then what's the length of the string? And I'm looking at the length now because it's all zeros, so there's no point in looking at the string itself. We only need to look at the length of the string. So the length of the string is what? Well, we started off with p squared zeros, right? Well, by putting an extra copy of y in, which has length beta, how long is the string now? Plus, how many beta? One beta, right. Because I'm putting one extra copy of it in. So the length is p squared plus beta. You could choose I equal to 3 for this problem, and it'll actually still work, but I equals 2 is just fine too. Okay, but let's see. How did we prove that this number is not a perfect square? We'll actually see it in more detail here. So what do we know about beta? Right, so we know, what do we know about beta? We know that beta is at least 1, for sure. Okay, cool. So that means, or at least it implies, that p squared is strictly less than p squared plus beta because it's at least 1. Cool, so it's not equal to that perfect square. No problem. But could it, in principle at least, be equal to a higher perfect square? It might be. So what else do we know about beta? Well, we know how small it can get. Is there anything about how large it can get? Yeah.
Because of xy, it can only be as big as p.
Right, exactly. Because xy has length at most p, that tells us, well, if x was the empty string, for example, that tells us that beta is at most p, by definition. So this number, p squared plus beta, is less than or equal to p squared plus p. By definition, if we just substitute beta less than or equal to p there. Well, what is this number, or this quantity, p squared plus p, in relation to a perfect square? Well, what's the next perfect square after p squared? Yeah, p plus 1 squared. So let's actually calculate that. So p plus 1 squared, if I just FOIL that out, what does that end up being? Yeah, p squared plus 2p plus 1. Oh, wait a second. Look at those two numbers. The one that, the largest that our string can get versus the other one. Can those ever be equal? No, and you can actually tell because of the plus 1 at the end. So this is strictly less than, I'll actually just write it like this, p plus 1 squared. So wait, the length of our string is p squared plus beta, but that can't be equal to p squared, and it can't be equal to p plus 1 squared. Is there a perfect square in between those two? No. So it's not a perfect square. Aren't you guys getting goosebumps like that? Because I am right now. So yeah, it's not equal to either of these perfect squares, and there's none in between. So since p squared plus beta is strictly between two perfect squares, it is not in L, and then that implies L is not regular. So now you know it wasn't just a useless exercise. It really did have purpose back in lab 1. Any questions about that proof? So yeah, you could choose I equal to 3 here. Then the length of this string is at most p squared plus 2p. But then that's still less than p squared plus 2p plus 1. So that one would also work. Yes, you would get the same conclusion. But if you tried, say, I equal to 4, then you can't guarantee it's between two perfect squares for that reason. So this is a case of where there are some values of I that work and some that don't. A lot of the time, most values of I work, but it's just you only need to show that one works. And in fact, sometimes there's only one choice that works. But any questions about this proof? One thing that I find really interesting is, suppose you wrote a program that you take in a number and you want to verify if it's a perfect square. So if you take the square root of a number and just check if it's an integer. There is no DFA to check if your program is correct. Because if it checked if your program's correct, it would be able to solve this problem, but it can't. Isn't that trippy? That you can just show that a DFA has really limited power about being able to show that your program's correct. But we're going to actually do one more along those lines. What is a really important set of numbers that you encounter all the time, and you have to check whether something is this? So like in communication or things where you need a number of this form, prime. So you may have been asked, I'm not sure if you've been asked about like in 101 or something to write a program to check if a number's prime. How many of you written a program to check something like that? So you may want to know, could a DFA or something check if my prime program is correct or not? Did I actually implemented it right? So you may want to look at the language 0 to the p, where p is prime. So what do you think, regular or not? What can you guess? It's not regular, sadly. This is actually a really hard language to recognize, as we'll see in the next coming weeks. But yeah, so this is actually not regular. And the heuristic argument from before about there being different gaps between the lengths of the strings, that actually is kind of similar to this one as well. So this is actually a really interesting proof because every single example that we have done so far, we picked I equal to 2. We picked I equal to 0. We picked an absolute value for every decomposition. We picked 2 or 0 or something, a fixed value. What we're going to do here is we're going to have the value of I depend on the decomposition, which is kind of weird. So it could be a different value of I for every decomposition, which is really interesting. But let's actually do this. So what do we need to do first? Let's go through the motions, yeah. So assume L is regular and there exists a P for L. What do we need to do next? Once we know there's a pumping constant. Yeah, just pick a string. What are the two properties that it needs to? Language and at least P. Don't do this. So the string I'm going to pick is 0 to the P. P stands for prime. It has length at least P, therefore it's in the language and has the right length. Right? P stands for prime, right? Oh, it doesn't? Shoot. What can go wrong? Is P prime? It might be. I have no idea. Shoot, we're already dead in the water. What can we do? Well, we gotta pick a string of length at least P. But does it really matter what the length actually is as long as it's at least P? No, it doesn't matter. So we need to pick a prime number that's bigger than or equal to P. Do we know if one exists? Yeah, how do we know? Remember the other question from lab 1 about the number of prime numbers? How many prime numbers are there? Infinitely many. So it can't be that all infinitely many primes are smaller than P. There must be a prime bigger than P. So let's not do this, let's do this. So the string we're going to pick is 0 to the R, where R is any prime at least P. Okay. So now we have a string of length at least P, and it is in the language now. So we're all good there. Except I'm going to make one tiny adjustment that turns out to be really important. And I'm going to do it in a different color so you know what the difference is. So here, instead of at least P, I'm going to pick it at least P plus 2. And you may think, that's just such a small difference. Who cares? It's at least P and you got a prime. Well, here's the thing. If we want to leave this language, what do we want? We want a string that is not a prime length. So suppose I give you a number that's not prime. What do you know about it? Divisible by 2 things, at least 2, and are not equal to the number itself. Where do you think that plus 2 comes into play? It comes into play by being one of the factors of the length of the string. Isn't that cool? So we can do that because it's still at least P, but it guarantees that the length will be divisible by 2 things, at least 2. So let's look at this. Well, if we look at the other proof, we saw that P squared plus beta, we knew that 2 would work because it was between two squares. And if we wanted to, we could not choose an I at the beginning and then just see what are the valid values of I so that we're still between two perfect squares, and then determine what I should be at the end. Here, we don't really have that luxury, because if I choose I is equal to 2, well, there isn't really much information to tell me if p squared plus beta is not a prime. So what we're going to do here is we're going to just look at the general situation. If we just pick some arbitrary value of I and then mix it around a little bit until we get something that is a number times another number, and then plug in the value of I so that we get something at least 2 times something else at least 2. So let's look at this in the general context and then pick the value of I later. So let's look at x, y to the I, z in the general case, and then we'll pick the value of I at the end. So again, like the previous proof, do we care about what the actual string is, or do we care about the length of the string? Doesn't matter what the string is, since it's all zeros? No. So what we're going to do is we're going to look at the length of the string, because it's just way easier to do it that way. Okay. I'm going to do 2 controversial things. So, and I want you to tell me whether we're justified in doing this. So we're looking at this. I claim that this is equal to the xz part just put together, plus, so the length of xz plus the length of y to the I. Yeah, why am I justified in doing that? Well, if you take the y to the I part and just put it over here, it's the length of the first part plus the length of the second part. So that's not too bad. Here's one more that's a little bit more controversial. So I'm still going to have the xz out front, but here I'm going to have plus I times the length of y. Okay? Why am I justified in doing that?
That's not really an exponent, it's just how many times y you use it, so it's basically multiplication.
Yeah, it's just the number of times that y appears. Okay, so no harm here. So then you may be thinking, okay, where is the 2, something at least 2 times something else at least 2 happening? Ryan, I'm getting impatient. I want to see the end of this proof. Here it is. So what do we know about xy? So let's put a little thought bubble down here. So what do we know about the length of xy? Well, less than or equal to p. Cool. Now here's the trick. What do we know about the length of z now? Based off of that fact. Well, the length of the string that we started out with is p plus 2 or more, right? Because we picked something at least p plus 2. What do we know about the length of z? Because the first 2 parts are at most p characters. So that means, well, since the string started out with p plus 2 characters, what do we know about z? It's at least 2. So that is the trick here. That's why we picked 2, if I can draw 2 right. The length of z is at least 2. So, well, that means, for instance, well, x could be the empty string, but we know that the length of xz together cannot be any less. So again, the length of xz is at least 2. What do we know about the length of y? It's at least 1. Well, how do I get something that's at least 1 into something at least 2? What's the easiest thing you can do? If you have something at least 1, I want it to be at least 2. You're thinking too hard. Yeah, add 1. So, well, the xz part's at least 2, and if I added 1 to y, that's also at least 2. So if I had something like this, so I'm putting a question mark here, because this is not justified yet. If I have something like xz's length times 1 plus the length of y, well then the first part, the xz part's at least 2, and the 1 plus y part's at least 2. So therefore, it's it must be a composite number. It's not prime because it's multiplied 2 things at least 2. Well, in order to go from that second step to the third one, what do we need to do? Because it wasn't justified in doing that. What would we need to do in order to get from step 2 to 3? What variable do we need to set? Yeah, set I. So that means we need to set I to be something. Well, what does that something have to be? What did we factor out of the length of xz? And we know that this is at least 2, this is at least 2. So therefore, x, y to the I, z is not in L. Therefore, L is not regular. And then you go, what? Where did that come from? So the goal, so I defy you to be able to come up with a proof like that on like an assignment or a test or something. So this is not to be like, oh, here's a problem that you're likely to see. You're not going to see a problem like this. I guarantee it. So what I want you to think about is in every problem other than this one, we chose the value of I to be universal among all decompositions, to be 2 or 0 or whatever. Whereas here, it depends on the decomposition. So as long as we pick a value of I, depending on the decomposition, and we get out of the language, we're all good. So that's what I want you to see out of this. Not like, oh boy, we're going to have to do this on a test. No, you're not. I guarantee it. The ones before that are more likely to be ones you'd be tested on. This one is above the pay grade, so to speak, for this. But any questions about how the proof went? Yeah. Yeah, so remember the language is about prime lengths. So the string that we ended up at, or I guess forced in order for it to work, is the length of the string is some number at least 2 times another number at least 2. But that can't be prime. So therefore it left the language for that choice of I. So by forcing the value of I to be this, that forces the string to have a non-prime length. Okay, any other questions? Okay, I'll see you on Friday.